Oh, supervised machine learning can be divided into supervised and unsupervised learning. Supervised does not require labels, so it's considered more smart. And if you are discrete data with unsupervised learning, it's called clustering. Otherwise, it's your continuous, and unsupervised is called dimensionality reduction. It's usually used for dimensionality reduction. Here's a scikit-learn graph. We now are talking about these two parts, the clustering and the dimensionality reduction. So let's see what's the most popular algorithm for clustering. It's actually called k-means. K-means try to partition, so split n samples into k clusters. Each sample belongs to the cluster with the nearest mean. That's why it's called k-means. Of course, if, so here's the idea. You randomly assign means. But first, you need to know how many clusters is in your data set. How many clusters are there in your data set? Otherwise, you need to guess. So once you have the K, then you can randomly assign groups and then calculate their mean and then update their value using their mean. So now in this case, assign each sample to a cluster and then recalculate the mean until it converges. So let's see an example. Suppose we have a black square, grayscale square. So we have a data set. Black block are the data. And then we assign k is equal to 3. So we have 3 means. So we randomly assign 3 means, right? And first we divide, we calculate the distance. So if this block is close to red circle, then it belongs to the class red, right? Others are close to green, so they are be classified as green. And the other parts are blue. And then we use those data in a group to recalculate the mean. So we recalculate the mean of each group, right? Then we reclassify. Now for the second iteration, our group red has two data, right? 2 data in the red group. The second iteration. Yeah, so that's the idea of k-means. So you repeat this process until you are satisfied, or until the means does not change a lot. It's not k-means. So here's a dynamic image, show you how the k-means used for, I think it's iris flower, did I say? So it's a simple and a very effective, very useful, yeah, I say. Okay. Also, let's try to do k-means, but k-means is simple. Like it's bad for nonlinear data, non-separable data. So here is the original class. Some class cannot be easily classified, right? The Virginica and the versicolor are mixed with each other in a vector space. Right. But if we do k-means, k-means will make all the data as one class. So since this is Virginica, he cannot, as you know, the means in the middle, so he cannot distinguish data like how to say it, interleaved with each other. And then is another problem is that k-means is split cluster here. But in practice, we want The answer is in the right side. The answer is in the right side. We are so K-means failed in this case. K-means failed. Failed in this case. But the K-means is still very useful because it's simple, right? And if good initialization, you can do many things. So the applications include vector quantization, cluster analysis, or feature learning, right? So problems of K-means that is sensitive to initialization, and it's also sensitive to outliers. Of course, to handle outliers, you can not only use means, but also use medians, right? Median class or mode. So there are K mode, K medians. Just depends on the statistics you select. And so also you need to make a harder assignment. So each class need to assign to what of the class? So it's work well only for round shape equal size cluster. So that's important. So it's work well for round shape equal size cluster. It's the best suitable for K-means. So to solve this problem, we have another problem that consider the interactions between data. It's called spectrum clustering. So suppose we want to separate two groups. Those two groups look like this. One is a circle, and another one is circle inside a big circle. K-means will split. K-means will split the data set because you will find the mean here, right? However, with spectrum cluster, you can successfully consider the distance between samples, right, and then separate correctly, like this one. So how can we connect? How can we consider the distance between others? So we can use the graph. Here's a graph that I made by which tool? It's created by me using Python. Anyway, so to make a matrix, we to consider the distance or connections between data. So we need to define a matrix. It's called the Laplacian matrix. So for a graph, first we care about the d's degree. A is the adjacency. Here's adjacency. Degree means how many nodes are connected with you. So for the first node, there are two connections, 5 and 2. So degree is 2. For the second is in this line, second row. You have 3 connections. So the degree is 3. The third row is 2. Degree usually means the importance of your node. It's how popular, how many friends are connected to you, right? And there's an adjacency matrix, so it means that here means 1 and 2 are connected. Okay, so it's asymmetric. If there's no direction, 2, 3 are connected, then it's 1. And Laplacian means the degree matrix minus by the adjacency matrix. Then we can use Laplacian to do clustering. The Laplacian matrix, we normalize like this. And yeah, so we can actually calculate eigenvalue of the Laplacian matrix and use the eigenvector as the cluster, something like that. Okay, so another method is the mean shifter. So problem K-means is one of the problems is that we need to know the number of K before do clustering, right? Well, we can try to, let me open this. In practice, we can use multiple probability distribution.
Mean shift is a method that's easiest to introduce when we do segmentation. The idea is, in mean shift, is to find the modes of a distribution or of a probability density. So remember, the modes are sort of the peaked areas. And here's the basic underlying assumption. The assumption is I've got a bunch of samples that have been drawn from some probability distribution function, and you want to find the modes. So there's this beautiful, couple of beautiful examples out there on the web. Feel free to steal whichever one you want. I stole this one. So here we have a set of particles, and they're just drawn from some density. And probably if I were to ask you where is the mode, you'd probably say that it's somewhere around here. Okay, and the goal is for the system to find that on its own. So here we have, again, we have our sample. So let's put down a region, okay? It's called a region of interest. Now, we're not going to talk about the size of that region just yet or its shape. We'll talk about that a little bit later. It's going to be a Gaussian. But for now, it's just going to be a circle. So we have this region, and we calculate, okay, of all of the points in that circle, where is the mean, or the center of mass? And we say, oh, it's not right in the middle. And that difference between them, that's called the mean shift vector. So this is called the mean shift algorithm. Amazing, huh? And so what do you do with the mean shift vector? Well, you shift the mean. And there it goes. Da-da-da-da-da. Perfect. Okay? What do? We do it again. Okay? Here's where we are. Here's the weighted mean of the new samples. There's our mean shift vector. What do? We shift it again. Ta-da! And we do it one more time. There it is. Oh, we're getting close now. Small mean shift vector, shift. And then finally, guess what? We are in the right spot.
Okay, so
Okay, so we get the idea of mean shift, right? Let's try to trace the area with the most number of data. So if we are not sure how many clusters we have, we can use the multiple probability distribution, like Gaussian distribution, and then use mean shift, right? So then they can move. Where's the animation? So maybe they will move together. They will trace moving to the mode, to the most density area. And once they are overlap with each other, then we can calculate how many clusters we have. Yeah. So, okay, so there are many different kinds of algorithms. And here's an example from scikit. So for each row, they have different distribution of data set, right? You can say the two circle, and the k-means will split the circle. However, the spectral clustering will successfully separate data. So from this picture, you can see how different clustering methods can work against the different distribution. So k-means the best, k-means work best for this kind of distribution, right? Okay. So finally, we briefly introduced the dimensionality reduction. Oh, actually, most common method for previous reduction is the principal component analysis. It makes some assumption that the data can be represented by linear functions in reality, and the mean and the variance are sufficient statistics, how it will calculate the covariance of different data. And then finally, the principal components are orthogonal. So they will here try to write the optimization function of PCA. Oh, so in this part we try to maximize the covariance of the data, and data is linearly, data y is represented by x and the w. Also linear representation of the data, and we want to maximize the covariance, which means the substrate true that the principal components are orthogonal, so which means they are with and matrix is multiplied by itself is an identity matrix. Okay, so another example is eigenvector, right? So eigenvector is try to project it's your PCA, so project data along different principal components. Deep learning for deep learning, unsupervised method is called autoencoder. Autoencoder try to compress data into a small vector or code, and then try to reconstruct the same output with from a small embedded vector. So it's like an encoder, decoder, right? Here is the encoder, try to make things smaller, and then there's a decoder. So encoder usually have a compress large vector into small vector, and decoder will decode it back. So by using this data, you don't need labels because you just try to make x equal very similar to original x, right? Right. Once you succeed, you will have a very good embedded vector here. So it's a encoder decoder, very useful. So popular in machine learning. Okay, so that's it. So I hope it's useful, and well, yes, let's make the less the raw coding we can dismiss. Okay. Okay, so next week, we